Hello students, so welcome to the third class of biomolecular spectroscopy. We were discussing theory of absorption of light by molecule and how the light or electromagnetic wave propagates through the space. Right. So, in this lecture what we have seen, the first thing we started that seeing is a spectroscopy, like whatever we see through our eyes, an object, the light is shining on that object, some image is created because light gets reflected, absorbed, scattered, and that our eyes has detector that detects and make an image. So, that image is created in the brain, and that is how we see or visualize any of the object. Right. So, in simple term, spectroscopy is nothing but light matter interaction, electromagnetic wave or light shines on the matter and interaction happens, and that is what giving some property which we detect or visualize. Now, electromagnetic radiation can be seen as a wave or a particle. So, because of the wave nature we have certain kind of spectroscopy that we discussed, and as a particle nature there are certain kind of spectroscopy like photoelectric effect or so we have discussed. Now, we also discussed that in any matter there are different energy level and those energy levels are discrete. So, there is a energy gap between, like there is a gap between those. So, if say here is a gap between these. So, if your electromagnetic wave, right. So, this is the energy gap delta mu. If your electromagnetic wave matches with this delta E, so h mu, then the absorption happens, and that is what is the basic phenomena of spectroscopy. Now, we also quickly looked at what are the energy contribution. So, we are going to extend upon what we discussed in the last class, and in this class we are going to look at how we can harness the light to reveal invisible. So, using like our eye we can see many things which are visible, but there are many particles which are invisible. Those can be also seen if we use the simple concept of light matter interaction. That means, shining the light electromagnetic wave on tiniest object that we know in chemistry or biology, and we can look at their property, right. So, we can get an insight of UV absorption, how DNA is measured or how you measure the protein concentration or so. So, that is what we can do light matter interaction. Then we also looked at the how IR is IR absorption can detect the functional group in the object. So, chemical or atmosphere and tissue, and how we can check the drug purity by analyzing the absorption fingerprint. So, these are some of the some of the use of spectroscopy that we can see, all the way from measuring the concentration of biomolecules like DNA or protein, or analyzing the chemical moiety that is present in atmosphere or even in tissue, right. So, the explanation that we can give how we can do that every application, whether it is in medical diagnostic or pollution monitoring, it depends upon some kind of absorption, molecule absorb, and therefore, whatever the phenomena that we see can be detected, understood, analyzed and quantified. So, this is the light matter interaction, and that is what we obtain from here. Now, how we do that? So, we know that in any object there are energy levels, and if suppose this is my energy level, say here is the ground state, right, ground state, this is excited state. So, here we call it ground state as a S0 and excited state as a S1, and then another excited state as a X2. Now, in this energy state, the particles or the population of say electrons will be distributed here and some more here, something like here, right. So, that is what distributed according to a formula or distribution concept which is called as a Boltzmann distribution. So, it says that the ratio between upper and lower state depends upon what is this delta E between them, delta E between upper state and lower state, and what is the temperature. So, that T is temperature. So, temperature in Kelvin, and this is Boltzmann constant, right. So, the particles are distributed according to the Boltzmann distribution. Number of particles in the upper state and lower state will be different. Typically, say lower state particle will be more than upper state, but how much difference it is depends upon this distribution, which is called Boltzmann distribution. So, when we raise the energy, say thermal energy, more particle can go from ground state to excited state. Depends how much thermal energy is given, so that this gap is filled, and a smaller gap in this between two state means that like the difference between the population these two states is going to be smaller. If the gap is larger, that means more particles are in the ground state compared to excited state. So, that means as we have seen, this is our ground state, say S0, this is our excited state S1, and this is my delta E, right. So, if delta E is small or T is larger, that means exponential delta E by kT will approach to E by 0, right. That means which is 1. That means if your delta E is small and kT is large, so that means energy difference between the ground state and excited state will not be too much. So, if you just go back, you will look at this term becomes 1, that means N upper and N lower ratio will be 1. That means the number of particles in the upper state and number of particles in the lower state will be more or less equal. So, let us take a case for nuclear spin, right. So, the population of excited state and ground state are nearly equal, not much difference, because the energy gap between the upper state and lower state, ground state S0 and excited state S1 in case of nuclear spin is very minimal, right, and therefore, that N upper by N lower is not that much. So, in 1 into 20,000, that is the difference between ground state and excited state, right. So, a different electronic orbital are often large energy gap. So, if you look at electronic orbital, this is the energy gap. Therefore, the more particles are going to be in the ground state and comparatively quite less particle in the excited state. So, what is the consequence of this? So, if you take a realistic term to understand the consequence. So, if for 1 mole say K can be replaced by R, and that is gas constant. So, you can put all those, and RT at room temperature is 2.5 kilojoule per mole, right. So, that means if we put it all these numbers, what we can say that here is our electronic spins, here is delta E, this is our nuclear spin, this is our delta E. So, here if I have 5 particles, here we can have 2 particles, but in nuclear spin if here are some 5 particles or 6 particles, here will be say 5 particles, not much difference, right. So, therefore, in the electronic state, because of this population difference, sensitivity will be going to be more compared to the nuclear spin, and this concept we are going to understand more as we move further, right. So, the larger the gap between the ground state and excited state, more population are going to be in the ground state compared to excited state. If the energy gap is not much different between the ground state and excited state, the population difference is also going to be very small, right. So, this is our electronic spectra, this is our nuclear spectra, that is the analogy you can have. Here the energy gap is quite large, here the energy gap is small. So, population difference is large here, population difference is minimal here, right. And to fill this gap, like, or here is delta E. So, if I have to do a spectroscopy, delta E, say I write nuclear and delta E in electronic state. So, basically when we are doing spectroscopy, what we are doing? We are exciting the particles from ground state to excited state, whether it is case for nuclear spin or electronic spin. So, to excite this one nuclear spin or excite this one electronic spin, you require a different kind of electromagnetic wave, because what we are looking for, delta E equal to h mu, right. H is constant, Planck constant, and mu is the frequency. So, for this delta E, which is larger, you require a larger frequency. This delta E, which is smaller, you require a smaller frequency. And therefore, if you look at the electromagnetic wave spectrum, essentially what we found, that depending upon what is delta V, we choose different kind of frequency to excite the energy gap or do the different kind of spectroscopy. For UV visible spectroscopy, our frequency range are going to be 10 to power minus 15, for IR 10 to power 12. When we come to the nuclear spin, which is in the radio frequency, it is going to be megahertz to kilohertz, right. You require less energy in this case, you require much more energy in that case. Therefore, the radiation source that will be chosen for doing different kind of spectroscopy is also going to be very different, right. So, in this case you require visible UV visible range, and therefore, frequency is going to be 10 to power 15, in this case 10 to power 6 to 10 to power 3, right. So, that is the difference of energy that is required for doing particular kind of spectroscopy. Now, in the last class we have written that this is electronic state energy level distribution. We have a S0, S1, S2. Between electronic state, what we had? Vibrational state like a V1, V2, V3, V4, and in each electronic state that V1, V2, V3, V4 is there. And then in each vibrational level we had a different rotational level. So, if you look at here, the rotational level gap is quite small compared to vibrational level, and that is quite small compared to your electronic state. So, delta E for doing electronic spectroscopy is much more than doing the vibrational spectroscopy than rotational spectroscopy. Now, going back here, so if we want to do electronic spectra, your delta E is larger, therefore, h mu, that means mu has to be larger, that is what we have 10 to power 15. Then vibrational spectroscopy, the energy gap is smaller compared to the electronic state, therefore, mu is required 10 to power 12, and then microwave 10 to power like 10 to power 9, that is for rotational spectroscopy. And finally, electronic spectroscopy like NMR, nuclear magnetic resonance, you require a frequency of 10 to power 6. So, that is the correlation between what kind of EM wave we need for doing a particular kind of spectroscopy, right. So, that is what we were discussing. For UV visible, since the transition is happening from electronically ground state to electronically excited state, you require large energy gap compared to vibrational spectroscopy, right. So, to sum up everything that we have discussed so far, so how does population difference in NMR compare with the difference between electronic state, electronic ground state and excited state? So, if we take this value, say we are using a lambda of 600 nanometer, that's if I go back here, you can see in this range UV visible radiation region, and for NMR you require radio frequency level, so 10 to power 6 or 10 to power 15, that is the thing. So, if you are taking 600 nanometer light of wavelength, it has a frequency of 5 multiplied with 10 to power 14 cycle per second, that is a hertz, and energy that will directly proportional to its frequency, and Planck's constant we know 6.623 into 10 power minus 34 joule per second. So, the h mu for the 600 nanometer light will be this much, 3.31 into 10 power minus 19 joule. This is almost equal to the energy spacing between the ground state and excited state, that is delta E, right. That is for electronic state. Now, coming back, same calculation for a hydrogen nuclei in nuclear spin. So, if we are putting this hydrogen nuclei at 11.74 Tesla using say gyromagnetic ratio of hydrogen normally referred as proton, we found that after doing all these calculation of delta E, energy is this much, right, 1.054 into 10 power minus 25. How much was for electronic state? If you just compare 10 to power minus 19. So, this is 10 power by this difference is 10 power minus 19 divided by some x into 10 power y multiplied with 10 power minus 25. So, at least 10 power 6 time more energy, that is energy gap that is there in electronic state spectroscopy compared to the nuclear state spectroscopy, and therefore, you require powerful radiation to irradiate that. That is what one can think of the energy gap that we are seeing between the electronic state and nuclear state. So, to sum up here, like if first of all, like an electromagnetic wave that we are using can be used to do multiple kind of spectroscopy. Which frequency or which wavelength to be chosen, that depends upon what is the energy gap. Typically, for electronic state energy gap is more, compared to that the IR spectroscopy, the vibrational spectroscopy energy gap is less, and then rotational spectroscopy even less, and like a nuclear spin spectroscopy like NMR, nuclear magnetic resonance, even smaller. So, like 1,000,000 time more powerful radiation in terms of frequency you need if you are doing electronic spectroscopy compared to the nuclear magnetic resonance. So, sensitivity therefore depends upon what is the energy gap between the two states for doing a particular kind of a spectroscopy. So, sensitivity for electronic spectroscopy is always going to be much more than a nuclear magnetic resonance, or even vibrational spectroscopy will be quite higher sensitive compared to nuclear magnetic resonance. So, that is what is the difference between different spectroscopy that we are going. Now, let us start the basic concept of the UV visible spectroscopy, right. So, as we summarize, any radiation that is going to interact with a matter, the number of process can happen. So, when a light is coming and interacting with a matter, what can happen? The matter can reflect it, or it can scatter it, or the part of that light will be absorbed, and after absorption it can even emit back, that we call fluorescence or phosphorescence. So, it is absorption and re-emission that happens in fluorescence or phosphorescence, or this light can create some kind of photochemical reaction, that means absorbing and breaking the bond. So, these many phenomena are possible when a light is interacting with the matter. So, when we are measuring this UV visible radiation, right, when we are measuring the UV visible radiation, what we can have? So, all the energy gap that we are seeing will be coming from electronic state, the vibrational state, the rotational state, and many other state that we have discussed previously, but say these are the three prominent one, where energy for electronic state is quite a bit higher compared to vibrational, compared to rotational state. So, total these contribution comes, and upon interaction these are the phenomena that will happen: reflection, scattering, absorption, and after absorption it can be re-emission, which we classify as a fluorescence, phosphorescence, or after absorption it can break the bond, that is a bond breaking. To understand this energy level distribution and what happens, how these all phenomena happens, there is a energy level distribution diagram that has been given, and that diagram is called Jablonski diagram. So, Jablonski diagram is nothing but simple representation of energy level of different electronic state, vibrational state, rotational state, and all those. So, here whatever we are discussing, this is the foundation of Jablonski diagram. We start with a S0, that is a electronically ground state, then electronically first excited state, second excited state, third excited state, and so on and so forth. In each excited state, these are different vibrational levels, V0, V1, V2, V3, V4. Similarly, in S there will be V1, V2, V3, V4, S2 same thing, and S3 something. Then in between something called triplet state, we will come to that. how triplet state comes, but this is like a this is more stable than singlet state. So, triplet state it's defined on spin multiplicity. Here the 2s plus 1 is 1 and here 2s plus 1 is 3, that is why this is called triplet state, this is called singlet state. In a moment I am explaining you. So, the triplet state energy is between S1 and S0, right, and the axis on the state. So, energy diagram arranged in energy on a vertical axis and the spin multiplicity. That spin multiplicity defined that whether it is the singlet state or a triplet state, and transition happens typically, like if you remember briefly I mentioned Frank-Condon principle. So, in a vertical line and each of these energy level is given in horizontal line, right. So, the bold line represents electronic energy state like S0, S1, S2, S3, 4. The thinner line are vibrational V1, V0, V1, V2, V3, V4 and rotational line somewhere in between, but in this case just for simplicity I have removed. In the previous slide we had seen that vibrational state, in between vibrational state there are rotational state, right. So, I was discussing about spin multiplicity. So, you see we know from our high school that electronic spin can be up or down, right. So, in ground state suppose we have electron in spin orbital up and down, right. So, here what is the spin multiplicity? This is plus half and minus half. So, total spin multiplicity 2s plus 1 will be half plus half 0 and S 0 multiplied with 2 plus 1, that is 1. But suppose our spin here in triplet state both are up. So, that means plus half 1. So, 2s plus 1 now will be 3 and that is called triplet state. So, this is the spin multiplicity. In this case our electrons will be like this, and in this case our electron are going to be like this. So, that is the triplet state and singlet state that we had seen. Now, energetic convergence, what we see that as the electronic level increases, the spacing between, if you look at spacing between the state decreases, causes like a vibrational levels to converge or to match or overlap. This is called vibronic coupling, and at very high energy level separation basically disappears and that becomes a continuum, right. So, key design principle what we can think, while energy level can be quantitative, Jablonski diagram typically uses a schematic, not a scale to represent. So, this is just a schematic to make you understand or convince you how electronic transition will happen. If you go to S4, S5, the electronic levels will be more or less continuum. So, here this is the just representation to make you understand that they are discrete and the energy gaps really exist, but if you go to higher excited state more or less that gaps starts collapsing and it becomes a single state, right. So, what happens now? Let us look at how electronic spin starts departuring from the ground state, right. So, Jablonski diagram absorption what happens. So, to start with what we had, all the particles here and this is the energy difference between them. Now, when we shine and light, that means we are trying to match delta E equal to h mu, shining lights, that is what is happening. So, now our electrons from ground state starts to go to different excited state depending upon how much this h mu is given and which delta is matching. So, if S0 S1 minus S0 is matching with delta mu, they will go to first excited state, otherwise second excited state or third excited state. So, that is the diagram representation we can have, that transition typically represented the straight line upward, and when absorption happens the particle from ground state starts to go to excited state either S1, S2, S3 or S4. So, this is the Jablonski diagram representation, indicates that it is a very rapid radiative movement. As soon as they absorb the light, the electron goes up. only photon with an energy that is precisely matches. So, you have to see that photon like mu energy, that the photon energy which is carried by this h mu should exactly match with the energy gap that we have between S 0 and S 1 or S 0 or S 2 or S 0 and S 3, then only this transition happens. So, typically like here, this is our electronic state, it can go to S 1 or S 2. When it goes to S 1, the electrons are transitioning from S 0 to S 1. When it goes to S 2, they are transitioning from S 0 to S 2, and that is what they give the absorption. When they absorbs, like they absorb from S 0 to S 1, one line, S 0 to S 2 another line, and very sharp electronic transition spectra that we can get for an atom, and this is the line spectra that one can have it, right. So, that is what absorption happens in the brief. To sum up what we discussed, that in each molecule there will be electronic state S 0, S 1, S 2, S 3, and when appropriate light is shining on this molecule, the electron will go from S 0 to S 1 or S 0 to S 2 and so on and so forth, and that gives you a spectrum which you can plot it intensity versus the lambda, lambda is wavelength, right. And in atomic absorption spectroscopy you get a very sharp line. So, let us close it here and we will see what happens in the next class. Thank you very much.